Welcome to Internet and Cloud Computing under Professor Yang Cho. In this laboratory, we're going to take a look at fast, reliable file transfer over TCP/IP. This was a group collaboration, and these are the team members. Looking over the objective of this lab, it was to improve the TCP performance over a very high latency link with 200 milliseconds of delay and 20% of a loss rate. So first, we checked the TCP performance with secure copy protocol, and then we went into the kernel, we changed the kernel module, we recompiled it, we reinstalled it into our debtor nodes, node A and node B, and then we again tested for the TCP performance. For this, we had removed the exponential backoff and we modified the TCP stack, and we checked the throughput. So this is the objective of Lab 6. Moving forward, congestion versus lossy link. Now, TCP is a protocol which cannot differentiate if a packet is lost due to congestion or due to an unreliable lossy link. So many a times what happens is the TCP interprets that, oh, the loss is because of congestion, while it implements various congestion control mechanisms to avoid such congestion, but many a times it's not because of congestion. It can also be due to a lossy link. So what happens when a packet is lost due to congestion? It happens when a lot of packets increase in a channel and the router drops some of the packets and the packet does not reach its destination. So this is because of the congestion. But what happens due to the lossy link? There's a lot of delays introduced, there's some problems with the link, and due to which the packets do get lost. Therefore, the packet loss is due to a lossy link. So what happens due to all of these losses? The throughput decreases. And when the throughput decreases, we need to retransmit these lost packets, and it becomes it's the same process as transmitting a packet again. We performed the experiment for 0, 10, 15, 20, 25% of loss, and we measured the throughput according to the delay. So we gave different delays and we measured the throughput. So in the start, let's look at 0% loss and 10 milliseconds of delay. This is the NS file, and let's look at the terminal. All right, so I'm already in my node A and my node B. I'm going to use the dd command, and by using this dd command, I'm going to create a 100 MB file. So this is just for the demonstration purposes. When I was doing the experiment, we had created a 1 GB file. So just for the demonstration, let's use 100 MB file. So by using the dd, if is equal to, so it's input file is equal to dev urandom, which means it's a random file. OF output file, the name that I'll give is data.bin. BS block size 1M, count, as it is a 100 MB file, it's going to be 100. Okay. So this may take some time. When we were doing for 1 GB, it took a longer time to create. So it shouldn't take as long to create a 100 MB file. As shown, it's created. Now using the scp command, we're going to be sending this data.bin that we have just created to node B, and we're going to see the throughput. Ch node B. it's better to use the qualified name. It's not always preferred. If you don't use it, it can still be transferred, but I prefer using it. .net :temp as I've wanted in my temp folder. So you can see here that the data.bin file was transferred and we got a throughput of 33.3 MB per second, but when we are transferring 1 GB file, we get a much lower throughput for 10, 15, 20, and 25. And we got stalling for 25% for almost all the delays. And the stalling took place because there is an exponential backoff. Like I said before, TCP uses many congestion control mechanisms to avoid congestion. But in this experiment, we just have 2 nodes and we do not need this exponential backoff, and due to which the stalling was.
So for modifying the TCP, on reading the research papers, it is found out that when we send a file of 4 MB, it can be sent without any packet loss, and the window size should be kept as the bandwidth delay product in order to get a good throughput. And it was discovered that on taking out the linear backoff and the exponential backoff from the TCP algorithms, we were able to achieve a higher throughput as the link had just two nodes on it and there was no other traffic from any other nodes. So there was just traffic between the 2 nodes, because of which we were able to remove the exponential backoff and the linear backoff. Also, we modified the sender window, receive window, and congestion window. For referencing the research papers, we used removing exponential backoff from TCP, where we found out that the RTO should be kept greater than RTT. On reading congestion control in IP TCP internetworks, we found out the Nagel's algorithm and learned about it. In the third paper, which was TCP and Linux pluggable congestion control algorithms, we got to know about the TCP implementations, which were Vino, Hybla, Cubic, and Vegas. In our experiment, we are using Vino algorithm and we have made some changes and modified it as well. Now, the commands which we used to get the Git repository, where we used Ubuntu Trusty, which is basically Ubuntu 14.04 32-bit. And for cloning, this is the command which we have used, git kernel ubuntu.com. And for getting the building the dependencies on the host system, we use sudo apt get build dependencies linux image 4.4.032, which is our version. And in order to clean the source tree, we have used Debian /rules clean. And for building the architecture dependent binary packages and the program, we are using fake root Debian /rules binary header binary generic binary for arc. We are using a 1 GB file and we are creating it using the dd command as shown over here. Now we have modified different files, and those are tcp.h, tcp congestion, tcp hybla, tcp output, tcp mini sockets, tcp timer, tcp vino, tcp input, tcp.c. And as I've explained that by using the following commands, we were able to compile the code on our local system, after which we got the Debian files which we recompiled on our nodes.
release of the Linux source code, of the modified Linux source code, we get a few files, specifically 6 files that are generated as DEBs. So before we install them on our nodes, let us look on what a DEB file is. So DEB is the format as well as the extension of the software package format for the Linux distribution Debian and its derivatives. So Debian packages are standard Unix archives that include 2 tar files, one which holds the control information and the second one which holds installable data. dpkg is a command which provides basic functionality for installing and manipulating Debian packages. What dpkg does is it replaces all the modified code into the kernel image which is existing, so that when we reboot the kernel, it basically uses the updated code. Once we push all the DEB to our nodes, we run the command sudo dpkg -i linux start deb. So that means it basically installs all the DEB files which are copied. Once all the DEB files are installed, unpacked and installed, we need to reboot the system for the changes to take effect. And then in some cases, in some corner cases, we went into some errors which can be solved using the following commands. So install update would basically update all the packages which are existing in the Linux distribution and then clean it. And then again -f install would rerun all the update programs so that when we dpkg, we'll have the right kind of packages to support it. Before we go over the results, let's go over the demo. Now, to show you the changes that you have made for the existing TCP stack, the way we are going to go over this is by comparing the two, comparing the pristine source code and the modified source code using beyond compare, where we can check file level changes. So the first change would be in tcp.h. Get the file, tcp.h. There we go. Here, for starters, we have modified the TCP window. We have multiplied by 2. So basically the window size would be twice the size. And also we have taken note that the window scaling should be increased because stacks do 16-bit math. And then also the fast retransmission of TCP. Usually TCP waits for 3 nacs before it retransmits faster. So we have made it to 1 so that it doesn't wait for a long time. And then the send retries, we've been added 1 so that it sends the send packet 6 times. The RTOs and the RTO max and the RTO min is reduced as per the instructions of the first paper reference. Now the window scaling is increased, it's doubled basically. Here it was 3 and then we've made it 6 because of the window size increased. We've disabled the Nagel algorithm and also increased the initial congestion window 100 times greater than the previous value. The next change would be inside the C files of IPv4, which can be found under the net folder, IPv4. In that, we see a lot of files written and then only a few files were modified. tcp.c for starters. Here, the timeout is unchanged for the retransmission. So this is one of the small parts of the exponential backoff. And so once there is, we know the concept of TCP, which is linear increase and exponential backoff. In this scenario, we have actually cut it down. In case there's a failure scenario, it doesn't go to 0. It basically goes back to the congestion window, which was 1000. So there is no decrease in the congestion window. We try to keep it constant. The same thing goes here as well. The next change would be in congestion.c. Right. So the congestion window is actually set to the clamp because we still want to keep it saturated. We don't want to take the minimum of both the values. We know that the congestion window would be a lesser value in most of the cases when compared to the clamp value. So we don't want it to be minimum, right? We want it to be the optimum value. Here, for the recent like a slow start threshold, we don't want to set it to 2 units. We want to set it to the congestion window units. And no changes in this file. Close. Right, so we have changes in this. Right. Okay. So the send congestion window is set to 1 initially, and the clamp is also set to a very low value. We don't want it to be cut back by many, like a significant fallback. We want it to be very small value initially, and then this as well. This was a minimum of both the send congestion window and the clamp. We know that the clamp would always be more in most of the scenarios, so we directly set it. Right, this one. Quick acknowledgements. We have set it to the max possible value, and then again the max of these two is already set, and the window is the receive threshold, the slow start threshold. Again, we need the max. We've set the max value, max possible value. Again, the max possible value. Again, we don't want the congestion window to be a small value. We want it to be saturated. We want it to be constant all along, so that even when there is packet loss, or if TCP thinks that there is congestion, let the congestion window be constant. Let's not go down. We still try to transmit the same using the same bandwidth. Instead of the initial congestion window, we want it to be the clamp window, which was set to a very high value initially. Right, so this is where we start the initial congestion window. This is where it starts from the linear increase and then the exponential back off. Then we have tried to modify a few places where it matters the most, like the TCP window. We're trying to use the max possible TCP window, which we try to override in lab 4. And yeah, so the same things, which messes up the congestion window to be the max possible value. And this is the maximum segment size, or the minimum segment size, which can be transferred. Right, so this is the reason, this is the logic where the congestion window is decremented in case there's packet loss, or in case the TCP times out. But we don't want that to happen, so we still keep it constant. Right, so here we still want the window to be a bigger value. We just override and set the max possible value of the window size, which we're using in tcp.h. This is the portion where we are removing the exponential backoff. Always returns 0. There's no backoff. We just try retransmitting at the very next instance. All the logic, all the ping pong logic commented out. And one of the last changes would be in TCP Vino, because in this experiment we are using the Vino version of TCP while we transfer the 1 GB file. Right. So initially, when the congestion window starts with 1 and 2 and 3, ramps up in a linear fashion, well, we want it to be quicker. So we, instead of incrementing by 1, we are basically incrementing by 3 every time there's a successful transmission. Just kind of an exponential increase in saturate at a maximum possible value. Right. After all these changes, let's go to the terminal, and then we'll try to compile the program, compile the changes. Right. So we have all the files. We make use of fake root, Debian rules, and clean. This basically cleans all the output files which were created previously so that we can freshly recompile the operating system code. Let's make use of sudo. Alt and clean. There we go. Okay, once this is clean, okay, the command to compile, then let's compile the operating system. There we go. This process would take around about 2 hours. We will fast forward the video and then see you again when the code finishes compiling, and which produces all the DEB files that are required. Once the operating system code compiles, it gives us 6 DEB files. We can find the DEB files are generated outside the source code directory. What we're going to do now is push these files to both of our nodes and then install them on the nodes. See you on Twitter then. Okay, we have copied the files to a folder inside our data lab. So we have 6 DB files which are on the virtual machine is now copied into the data nodes. Then if you have to install them, let's try to unpack. Then the way to do it is cd so we would have to run one simple command, dpkg debian package install start.dev. We install all the packages. We will do the same thing on this node as well. So both our nodes, both our both our nodes will have the updated Unix, the updated Linux source code. Let's run this command again here. Okay. Once they're installed, we try to reboot, and then once they reboot, we're good to go. The nodes are set to a delay of 200 milliseconds and a loss of 20%. And we will, once the system reboots, we will try to transfer 1 gigabyte of file and then check the throughput. All right, we've installed, so we do a sudo reboot here, and once this is done, we'll also do a reboot here. And for trial, before we tried the 1 gigabyte of transfer, we tried to transfer a 100 megabyte file from one node to the other using the same modified TCP stack, and we were able to achieve a throughput of 1.3 megabits per second, a little over the project requirements. So once both systems reboot, we will try to do the same thing now for a 1 gigabyte file. Right, so we will reboot this as well. Okay, since it takes a while for the systems to reboot, we will fast forward the video and meet you back after the system reboot. Created a 1 gigabyte file in one of the nodes, and let's try to transfer it to the next node right now. ACP data.usc and to be sent to node B and to the temp folder again, just in case. Let's go. That's a good start. We have started with 3 Mbps, and then it just kind of goes down a little in the middle, and then it goes even below 1 megabytes per second, and then it always comes back and stays around 1.4, 1.3. Well, the ETA is 12 minutes. We'll also wait till the transfer is complete, and we'll fast forward the video and come back once the transfer is near to finishing. End of the transmission, then we can see that the throughput is averaging out between 1.3, 1.2, and 1.4 megabytes per second. Right, there we go. So the final throughput is 1.3 megabytes per second, which would translate into, if we convert into bits per second, it's 10.4 bits per second. So we've tried multiple trials. We've tried more than 20 times, and we find that the throughput varies between 1.2, 1.3, and 1.4 megabytes per second. So on an average, for most of our trials, we got 1.3 megabytes per second. And then we can check that the same file is being received here in the data. So let's generate the MD5 sum, and then let's do the MD5 sum of data that you see again here, and we can see that this one and this one are the same. So this completes the file transfer. It was a nice learning experience since we got to go into the kernel modules, change it, found out how to recompile the kernel, install the kernel on a different machine. It was a very fun learning experience for us. And then finally, so this is what a throughput is, 1.3 megabytes per second, which translates to 10.4 megabits per second, which is 0.4 megabytes per second improvement. I mean, more than the limit set at the project, which is 10 megabits per second. This is the NS file which we used for the project. There we go. And finally, thank you for viewing the video. Please comment in case there are any improvements, and we're all open for suggestions. Thank you.